In this lesson, we're going to talk about histograms. So in the last lesson, we discussed different types of data, categorical data, quantitative data, and also quantitative data can be categorized as either discrete quantitative or continuous quantitative. Today, we're going to talk about continuous data and histograms. Let's talk about organizing continuous data. So here we have two different frequency tables that you can use to organize continuous data, and over here is an example of a histogram. Let's first talk about the frequency tables. Now, this particular frequency table here is like two different types. I think this one is a little bit flawed, to be honest, because you're measuring something here, and this height of something or other being measured in millimeters. And this particular class or group is saying that 12 of the whatever we're measuring is between 300 and 324 millimeters. But it doesn't account for if you're 324.4 millimeters. And the truth is that you really need to have like a less than or equal to sort of situation, where this would be 325. So you don't get into the next class until you are 325 exactly or more. And you'll notice in this one, whatever they're measuring here in centimeters, they don't even list the upper bound for that particular class. They just say if you're 170 to something, you go into this class. But as soon as you get to 175, you move up into the next class. And 180, you move up into the next class. And then here they're showing you that if you're less than 205, then you're going to fall into this class. So obviously they didn't have any measurements that were more than 2. And then over here, the histogram, it looks a bit like a bar graph or a column chart. But the main difference here between a histogram and a column graph or a bar chart is that there are no gaps between these columns here. And the frequency measured would go across the vertical axis, and the data values would go across the horizontal axis. So here we're just going to consider the weights in pounds of students on a rugby training squad. So this is the proper way to do the intervals for the different classes. In a histogram, we're saying between 110 pounds, less than or equal to whatever their weight is, less than 130. So as soon as you get to 130, then you get bumped up into this next group right here. But if you weigh 129.999, then you're going to be into this lower class right here. So is the data discrete or continuous, and why? Well, of course it is going to be continuous because it's a result of measuring something. You're measuring somebody's weight. So a few things about the frequency table. So each group is called a bin. You may have heard me just say class because I've worked with textbooks that would call this a class, but you can also call it a bin. The size of the grouping is called the bin interval. So like here, the weight interval is your bin interval. The bin interval must be the same throughout the table. That's very important. So you'll notice that this one, but the difference between 110 and 130 is 20 pounds. 130 to 150, 20 pounds. It wouldn't make sense for this bin or this class to go from 110 to 130 and the next one to go from 130 to 180, for example, because that would make your classes different sizes. You need those bins or those classes to be the same size. And generally you want somehow 5 to 10 bins. If you have fewer bins, then it's kind of useless, doesn't really help you classify your data into different groups or describe the data. And if you have too many, then it's basically like every class or every bin is going to have like a frequency of 1. So you don't want too few and you don't want too many. So here is the histogram of that particular data right here. So the rugby training squad, you'll notice that my horizontal axis is measured as weight in pounds, and then the vertical axis is the frequency. Another thing to point out is that the line segment where where these columns are separated, that is the dividing line for those bins or for those classes. So you're going to have a column that's going to separate at 110, 130, 150, 170, 190. So that's very important as well, that's where you're separating your columns. So what's nice about a histogram is it's very easy to use for large data sets. And it's very easy to see the shape of the distribution, which we'll talk about more about that later. But the bad thing about histograms is it does not show, just the datagram itself, it does not show every individual value in the data set. You're just putting people into groups or putting items or whatever into groups. So this is just a slide to show you the difference between a column graph where the columns are separated and a histogram where there are no gaps in your columns. So our first example, the histogram shows the heights in inches of some basketball players in a local competition. How many basketball players were involved in the survey? How many of the basketball players were less than 71 inches tall? And what percentage were 69 inches or taller? Pause the video here and answer these questions. Okay, so to answer these questions, you would have figured out or needed to figure out that there were 15 people in this category, 20 and 30. So I'm just looking up here and going across. So there's 40 there and there's 30 there and so on. I'll also point out that the way that this particular number line is done is really not ideal. You really prefer, that would be 63 there and 65 there and 67 there. So those are the different classes that are divided up like so. So how many total basketball players were involved in the survey? Hopefully you figured out that would be 140 players. How many of the basketball players were less than 71 inches tall? So 71 falls here. So you're looking at adding up all of those, and that is 105 players. What percentage of the basketball players were 69 inches or taller? So 69 falls here. So you would add up those 3 columns and the percentage. So we need the total of them. So that was 75 total that were more than 69 inches tall. And then out of the 140, so that makes about 53.57%. All right, next we have The weights of parcels, so packages, sent on a given day from a post office and measured in kilograms. So first we're going to make a frequency table and a histogram for this data. So you can see the classes are already, or the bins are already set up for you, that if the package was more than 1 kilogram but less than 2 kilograms, you're going to put it in this category or in this bin, and between 2 and 3 it's going to go in this bin, and so on. So what you may want to do is just kind of count them as you go. So how many of them were between 1 and 2? So I see 1, 2. So just 2 fall into that bin or that class. So carry on with the rest of this data. So these are the results that I got. So now I need to set up my grid paper here to make my histogram. So I see, first of all, the vertical, my frequency is going to go along the vertical axis. We can just use like a little lowercase f here. The highest number I need to show is 6. I have plenty of grid lines for that. So I'm just going to make each grid line equal to 1, but maybe I'll only label every other one. So 2. And then for my my bins or my classes, the highest I need to show is also 6. So we can just say that this right here, the origin is 0. So then we're looking at, I actually have enough space to spread this out a little bit. So I'm going to make each grid line equal to a half instead of 1, 6. But you can do it differently than me. You just want to make sure that your scale is even. So if you're going to take 2 grid lines to go from 1 to 2, then you need 2 grid lines to go from 0 to 1 as well. 1 to 2, we're going up to 2. So there. So something like that. And then to make it a little bit more obvious to see, because of the grid lines on the little graph paper, sometimes I will just do a little bit of shading in here to make it a little bit easier to see my histogram. And there we are. Number 3. Multiple choice. Pause the video and have a go at this one. So this question is, they mention a few of the different graphs that we have mentioned before. So stem plots are useful for extremely large data sets. That's not true. Histograms, the bars must not touch. That is not true. They must touch. Both dot plots and stem plots show symmetry, clusters, gaps, and outliers. That is true. Bar graphs can represent categorical and quantitative data. Interesting that that statement number 4 is not even mentioned anywhere in our answer choices, but I would say that that is true. So from our answer choices here, the only reasonable response would be E. Describing the data. When you have a histogram or a column graph or a dot plot, or as was mentioned over here in this question, even a stem plot, then you can look at the distribution of the set of the data. So let's talk about that. So distributions can have many possible shapes. So when we're looking specifically at a histogram here, so we're going to write down a few words here. We would say that this is symmetric, unimodal, meaning it only has one mode, and bell-shaped. And we're going to get to that in just a second, but I will tell you that what you would do is you would take the medians of each of these columns, which is the midpoint of each of the bins, right? And then you would actually connect them with a nice smooth curve like so, a bit like that. I didn't draw that very well, but that's sort of the bell-shaped curve that we're talking about there. This next one over here to the right, this one, you can notice that you've got more tall columns here to the left, and then you have very little data over here to the right. So we say that this is skewed right. And that's often very confusing for students because they think, well, most of the data is on the left. Why wouldn't you say that the data is being pulled or skewed to the left? So you have to think about where the tail is. So this would be the tail of your data. And so that's how you remember which direction is skewed. So that one is skewed right because the tail is to the right. For the next one over here, this is clearly non-symmetric. Non-symmetric. I mean, the skewed right is also non-symmetric, but when it's skewed right, we tend to just describe as being skewed right. But bimodal. Bimodal. You have one value here that has a lot of frequency, and then you have another one here that has a higher frequency. So even though the 2 technically would be the mode, is the one that occurs the most, it's also significant to know that the 7 also occurs more than the other numbers around it. And then down here, the bottom left graph, we would just say that is uniform data. It doesn't really look like much, but there would be a bunch of different columns in here. You'd have a bunch of different columns there that all have the same frequency, so that data is considered uniform. And then the one here that's underneath the skewed right curve, you can maybe guess that that one is skewed left. And then this last one here, it is symmetric. You can see the symmetry in the graph of it, and it's also bimodal. Clearly has 2 modes, and those modes, they look like they are the same height, so they are exactly 2 modes. So this over here is a nice image to show the difference between a symmetric distribution, a skewed right, or a skewed left distribution. So the thing about a symmetric distribution or a bell-shaped distribution is that the mean and the median are both going to be right there in the middle of that bell-shaped curve. But if your data is skewed to the right, and this one has a very slight skew, as you can see, there is a little bit more of a tail here on the right than there is on the left. In this case, the median is going to be a bit more toward the hump of the data, and the mean is being pulled a little bit farther to the right. So an example of this is if you're talking about salary of all of the employees, the salary of all the employees, say at Amazon. the CEO, Jeff Bezos, his salary is going to be way, way, way up here, but most of the employees, their salary is going to be here. So the mean is going to be skewed. The high salary of the CEO is going to be pulling the mean toward that tail. And so the mean is going to be higher than the median. This is also considered to be positively skewed. So skewed right is also known as positively skewed. And then over here for skewed left, sort of the opposite idea here is that if you have a lot of data down here on the left, then that is going to pull the mean way, way down toward that tail. So an example of that could be, test scores. If you have one person that got like a 20% on a test and everybody else got like an 80%, an 88, then, the mean is going to be affected by that one person that really bombed that test. So in that case, you would be maybe more interested in what was the median score of that group of tests. And then this one is also known as negatively. All right, so here is an old AP Stat free response question. So pause the video and have a go. So it just says, based on the histogram, describe the distribution. So you just want to say something like, so right here, the history of the dissolved oxygen. And whenever you're asked these types of questions, remember, you want to rephrase the question. So based on his, describe the distribution of, so you say the histogram of dissolved oxygen concentration in Alaskan streams or in streams with water temperatures colder than 8 degrees. See how all of that is repeated. And I know it seems really silly to have to repeat what's in the question, but this is a proper way to give a complete answer, is repeat that question and then say is unimodal and skewed left. So for our measures of center, you're probably familiar with these from middle school. You have your mean and your median and your mode. So the mean is what we think of as our average. When you add up all the numbers, you divide by the number of numbers you have. The symbol that we use for this for a sample is X bar. We read that as X bar. I'm going to also add on here that you can also use this symbol mu, and that is for a population. And the mean is generally a good representative of the data. If you're trying to describe a whole set of data, well, how did everybody do on the test? Yeah, they did all right. They got, the mean was an 85 or whatever. But as I mentioned before, the mean can be influenced by extreme values. The mean can be influenced by extreme value. The median is your middle number. So this is when your data has to be put in order, then that's going to be your middle number. Now, if you have an even number of data, then the median is going to be the mean of those two values that are in the middle. And the median is not necessarily one of the data set. It could be, if you had a value, if the two middle numbers were like 5 and 6, then the median could be 5.5 because it would be halfway between 5 and 6. Now the median is useful because it is not affected by extreme value. And the value that occurs the most frequency, of course, that is your mode. And so data can be bimodal, so you can have more than one mode or two modes, or data can have no mode. If all of the values occur have the same frequency as every other value, then it has no mode. And that doesn't necessarily mean that every value occurs one time. It could be that every value occurs 3 times. In that case, it would have no mode. The mode is always a member of the set of the data. The median, of course, not necessarily one. And I also mentioned over here, I did not mention over here, but the mean is also not necessarily one of the data set. And the mode is also not affected by extreme values. So we're going to try this example. If you want to pause the video and try it on your own, then do that. So this is sort of working backwards. It says the mean of the 10 numbers is 5.4. And we want to find the value of A. So what you simply need to do here is use your calculator to help you. We're going to do 4 plus 3 plus A, 8 and 3. We're going to divide it by how many numbers there are. 10 numbers. It says it right here in the question, 10 numbers. And you're going to set that equal to 5.4. You're going to want to multiply everything by 10. So you're going to have 54 equals whatever the sum of all of these numbers are plus A. That's going to be 50 plus A. And so 4 is equal to A. And you're going to want to find the median of those numbers. So that means that you're actually going to need to do a little bit of work because you need to put them in order. So those are my numbers in order. And then you've got 5 to the left and 5 to the right. And so halfway between 4 and 5 is going to be your median. So the median is 4.5. Let's talk about measures of spread. There are 3 main measures of spread that we will discuss today. We're only going to talk about 2 of them, range and standard deviation. So range is going to be the difference between the greatest and the least values. So it's a pretty simple calculation. You just do the maximum value minus the minimum value, and that gives you your range. The interquartile range, we're going to talk about that next class. Okay, standard deviation is the most widely used measure of spread. And the measure, what it does is it measures the deviation of each individual data value from the mean. So if you had a situation where the mean of some test scores was, say, 85% and the standard deviation was, say, 5%, then you could say that most of the scores were between 80 and 90%. So 5% above the mean and 5% below the mean. So if you scored something like a 95%, then you did really well compared to everybody else because you were way above the mean, more than one standard deviation above the mean. And then the larger the data set, the more widely spread the data, and vice versa. If you had a very small standard deviation, then your data is going to be less spread out. So we have this very scary looking formula for standard deviation. First of all, we have this symbol here, which is a lowercase sigma, and we use that for standard deviation. This is for standard deviation of a population, and so there's actually a little bit of a slight typo here, that would just be mu, because remember that mu is the mean of a population and standard deviation is going to be that lowercase sigma symbol. And then for a sample, we use x bar for the mean, and then we just use a letter S for our sample. So the thing about the mean for the population of the sample is the formula is totally the same for finding the mean. You add up the numbers that you have and divide by the total number of numbers. The standard deviation formula is slightly different for a standard deviation of a population versus a sample. So this is the one for the population. You're going to take each individual x value, you're going to subtract the mean, you're going to square it, and then you're going to add them all up. You're going to divide by the number of them that you have, and then you're going to take the square root. The idea behind taking the square root is that you are sort of undoing the squaring process that you did in the first place. Now, you might wonder, why do we even square them in the first place? Well, the idea of squaring them in the first place is to make positive anything that could be negative. So the difference between this formula and the formula for standard deviation of a sample, you don't need to know this, so don't write this down. You just divide by n minus 1. So when you do these calculations, you don't have to memorize either one of these formulas. You're going to do them all within your calculator. But you need to understand that that's why you're going to have a slightly different calculation between the standard deviation from the population, the one that's called sigma, and the one that's called S, that's the standard deviation for a sample. Before we get into calculating the standard deviation, let's compare. We have two data sets here. This one is a 35, 40, 45, and this one is a 10, 40, and a 70. Both of them have the same mean, or the same measure of center, which would be 40. But this one here on the right is obviously more variable. It has a lot more variety, or the range is higher for this particular set of data. So while they have the same mean, this one is more varied data set. So this is why when we are discussing a data set, we are interested in both the mean, about how the measure is centered, and also the standard deviation, about how the measure is spread. We might also be interested, of course, in the median. It's another measure of center. And we might also be interested in the interquartile range, or even just the range. Okay, so we're interested in all of these things we're trying to describe. So we're going to do one standard deviation calculation by hand. But like I said, you're basically going to use technology every time in the future. What I have here is a set of data here. We're going to call this the population. So we use that population formula. I put them here in this table. I add them all up. The sum is 35. We need to first calculate the mean. And I'm just going to tell you that the mean is 5. We're going to take each individual value and we're going to subtract it from the mean. So we're going to do 2 minus 5. So that's negative 3. 4 minus 5 is negative 1. Now we're going to square all of these values. So this column just says do x minus mu and square it. So when we square all these values, we're going to have, and again, the idea behind squaring them is that you are just trying to make all of your negative values, making them all positive. Instead, we're going to take each x, we're going to subtract the mean, we're going to square it. We just did that. Now we're going to do the summation of it. We're going to add them all up, and we're going to divide by the number that we have, and then we'll take a square root. So when I add them all up, I'm going to get 16. 16 divided by the number of numbers you have. There are 7 numbers, and then you're going to take a square root, and that's going to work out to be about 1.51. So doing this in the calculator, you're going to type your data in list 1. You're going to go to one var stats under the stat menu, and then you're going to look at the mean and the standard deviation. All right, so I'm in my calculator. This is a calculator app. It's not exactly the same as the TI-84, but it is very similar. And I just went to stat and into edit, and I just typed the data in list 1. Now we're going to go to stat, over to calc, and you're going to go into option number 1. One var stats is your one variable statistics. Press enter. And it's going to ask you, where is your list? It is in list 1. And then for the frequency list, we don't have a frequency list, so just leave that blank. And then on the 84, you probably have to hit paste and put your cursor on the word paste and press enter or something. I'm just going to go ahead and press enter. And then I can see, so my mean there was 5. You see the X bar. See it? Oh, there we go. You see that little lowercase sigma X, 1.51. That's my population standard deviation. Right above that, the capital S X, that's my standard deviation for my sample. So because this was a population data, that's why we're only looking at sigma X. And that's it.